All right. In the last class, we have seen that a conventional source of light is not suitable for pumping, optical pumping, a gaseous medium. That is because, I just very briefly explain you once again, that is because in a gaseous medium, there are a lot of empty spaces between atoms or molecules which make up gas. And a conventional source of light, say flash lamp or an arc lamp, where origin of emission of light is actually spontaneous process. That is why the light is emitted from such a source in all possible. Therefore, it is suitable only for side pumping. That is, the pumping is done through the side of the resin medium. This is the resin medium, and this is the pump source, which is the conventional source of light. And because there is a lot of empty space, therefore, most of these photons, which otherwise would be intercepted by this medium, would actually escape unabsorbed. Even those photons which may interact with the atom, suppose if this photon interacts with this atom, it still may not be absorbed because the emission weight of such a source is pretty white. This is the emission weight. And the absorption feature of this gaseous medium can be pretty narrow. So this is the absorption weight, and this is the emission weight of the source. So this is delta nu, and the absorption weight is much narrower. So delta nu can be much higher than delta nu. And therefore, if this atom happen to lie outside the absorption weight profile, if this atom, if this photon lies here, so this photon is this photon, so it would not be absorbed. It doesn't lie within the absorption feature of this gaseous medium. So lot of photon escapes, and even those which may intercept, which may be intercepted by the atom or molecule, that also may not be absorbed if it lies outside the absorption feature. Only the photon which is intercepted by the atom or molecule and lies within this absorption feature will be absorbed, very qualitatively speaking. And that is why a conventional source of light is impractical, is inefficient, as a pump source for a gas laser. And we have also seen that if a laser is used, a second laser is used to pump a gas laser, for this, both these disadvantages, that is, this disadvantage that light is escaping, majority of the light is escaping to the empty spaces, and also this mismatch, frequency mismatch of the source of light with the absorption feature of the pumped medium, both can be both these disadvantages can be overcome by going for pumping the gaseous medium by another emissions from another. That is because this laser gives a continuous beam of light, and so you can actually pump it through the end. You can actually, suppose this is your laser, it gives out a directed beam of light which can be directly employed for end pumping. So the chance that this will be intercepted by this absorbing atoms or molecule is pretty high. And the emission width of the laser is much narrower compared to a conventional source of light. Therefore, it can have a good spectral match with the absorption feature of the absorbing species. Of course, we have to choose the wavelength of the laser appropriately to have a good match with the absorption wavelength of this gas or atom, which is to be pumped. So today, we will see how this laser can be employed to achieve pumping of a gas laser. What are the hurdles and how these hurdles can be eliminated? What are the challenges and how these challenges can be eliminated? The first and foremost is how to couple this beam of light into the lasing medium. There are serious issues. Let us discuss. So first of all, the medium which has to be pumped, and after pumping it becomes an active medium because it is now fit to amplify light. That means it will work as a laser. Now for it to work as a laser, this active medium has to be placed inside a cavity. And cavity comprises of two parallel mirrors. We have studied them pretty well in a number of earlier lectures. So one of the mirror is a 100% transmitting mirror, and the other mirror is usually a partially transparent mirror. And as the light grows inside the cavity as a result of to and fro oscillation, the light that builds up inside the cavity, to couple out a part of this light, a fraction of this light outside, you make one of the cavity mirrors partially transmitting so that part of this light can be coupled out, which is the useful loss forming the output, forming the laser beam. Now, of course, in order to add stability to this cavity, we know that at least one of the mirror needs to be concave. Else, this will be a highly unstable cavity. Anyway, I will not go into those details once again, but you must remember one of the mirror needs to be slightly concave. So for example, we make it slightly concave. Now, we have to introduce the pump laser beam, that is the output from the second laser, into this cavity. Now, how do you do that? Before that, you must know that the output of the second laser operates at a wavelength which is different from the wavelength at which this laser would lay. Let us consider the typical energy level diagram. Let us consider the case of a 4-level laser. That means this is a 4-level laser system. So we have the source level, that is the ground level, into which all the atoms or molecule initially reside. So all our atoms or molecules are in the ground state. And then they would be pumped to the pump level. And suppose this wavelength is lambda 1 by which we pump it. So the laser that would pump it would operate at a wavelength lambda 1. Suppose this is a pump laser which would emit at a wavelength which is lambda 1. Now once it is pumped, then you know that this species would very fast relax to the upper laser. And then suppose this is our lower laser level. So the lasing transition will occur between these two, upper laser level and lower laser level, and it gives out an emission say at a wavelength lambda 2. So this works at a wavelength of lambda 2. And of course, the species, after they have made transition from the upper laser level to the lower laser level, quickly relaxes to the ground level so that they are once again available to continue the lasing process. So then this laser works at a wavelength which is lambda 1. Now you have to introduce this into this cavity. Now can you introduce it? You just use a folding mirror and put it to this. You cannot, because this will block this beam. So can you then put it through the partial transmitting mirror? Well, let us see. So let us just revert. This is the partially transmitting mirror, and this is the concave mirror which is 100%. And this is partially transmitting mirror, say its transmission 10%, so reflection is 90%. So our pump laser meets at a wavelength which is lambda. Now you can actually, let us assume that this partially transmitting mirror has some transmission at wavelength lambda. This is lambda. It transmits some part of lambda 1 into this region. So it enters and it pumps. Pumps means it transfers the atoms or molecules from the ground state to the pump level. And as they relax to this, you attain population interaction. So lasing begins at wavelength lambda 2. So it emits this light at wavelength lambda 2. But how to tap it out? Because you have to take this beam for some application. See, if this lambda 2 otherwise would be reflected by this and travel right into this pump laser, which may be actually quite harmful for the optics of the pump laser. But the issue is how we will tap out this pump. You cannot. If you try to intercept it, then and use another mirror to take this lambda 2 out, but this will block your lambda 1. It would not allow lambda 1 to reach your lasing medium. So this approach will not work. So how do you then make it work? Well, you may think of putting a dielectric folding bed as an intracavity. We use a dielectric mirror, and this is your pump laser, which operates at a wavelength of lambda 1. So lambda 1 was, suppose this dielectric mirror reflects and this is your output, which is partially transparent. Now, this actually lasers at wavelength lambda 2, but the dielectric mirror, the normal dielectric mirror, would not transmit one wavelength and reflect another wavelength. So most probably it will reflect most of this lambda 2 back. So an ordinary dielectric mirror, intracavity mirror, is also not going to work. However, a dichroic mirror remedy is use of a dichroic mirror as an intracavity coupling mirror. This will work. So what is a dichroic mirror? Dichroic mirror is a special kind of dielectric mirror that reflects one wavelength and transmits another. For example, you see, this is our input line, which comprises of two wavelengths, lambda 1 and lambda 2. And as it shines on this dichroic mirror, lambda 1 is, this mirror reflects lambda 1 from this incident light and transmits the other wave, lambda 2. And this property of dichroic mirror, that it reflects one wavelength and transmits another, comes very handy here. So how do you use it? See, use it this way. This is your dichroic mirror, which you are using in the intracavity mode. This is the 100% reflective concave mirror, and this is the partially transmitting output mirror. Now, your pump laser lasers at a wavelength lambda 1, and the dichroic mirror reflects that entire lambda 1 into the active medium. So this lambda 1 goes and it pumps the active medium to the pump level. This is lambda 1. And then they quickly appear at the upper level, and this is the lower level. Lower level because it is a 4-level level. So lower level is initially practically empty. So you are taking population inversion, and so lasing then would occur to wavelength lambda 2. So as lambda 2 starts oscillating, it will pass through. This is lambda 2 because this mirror reflects lambda 1 and transmits lambda 2. So a cavity is going to be formed at wavelength lambda 2 and it will be able to oscillate back and forth. And the light now would grow at this wavelength lambda 2. And so lasing would occur quite appropriately at this. You are pumping lambda 1, which can be easily coupled through this dichroic mirror into the active medium, and the lasing that occurs at lambda 2, for which this mirror is totally transparent, and therefore this laser will lase lambda 2. It's absolutely fine. The dichroic mirror will work well. However, there is still some problem. What are the problems? Problems of dichroic mirror is that it is very expensive. You cannot afford to lose it. You cannot afford to waste it. And moreover, it has a low damage threshold. That means it can be damaged very easily with even optical flux of not very high intensity. Because of this, the dichroic mirror is very prone to optical damage. More so as the overlap between the coating surface and the antinodal plane of the standing waves formed in the lasing cavity is inevitable. Let me quickly explain this. See, when a laser lasers, when a oscillation takes place, to and fro oscillation, then the waves propagating in the two directions actually interfere and form a standing wave as shown here. The standing wave has a nodal plane where the intensity of the optical flux, the intensity of light is 0. And while at the antinodal plane, the intensity is maximum. So you have understood this, that inside the cavity there is a formation of standing wave and because of that there will be nodal and antinodal planes. Now let us return back to this. So this is the cavity into which all these nodal and antinodal planes have been formed. Now you have to place the dichroic mirror somewhere in the cavity. And it is quite likely that this dichroic mirror actually overlaps. The dichroic mirror is placed here. This is your dichroic. So it actually very well intercepts with an antinodal plane where the optical flux is very high, intensity is very high. So already this has low damage threshold. The chance that it will get damaged is extremely high. So this is a major limitation of using of dichroic mirror. Well, it may work, but it is very likely that you may damage such mirrors very easily. So then, what is the remedy? Remedy is to make use of the reflection property of light at Brewster angle. We have already seen in one of the previous classes where we discussed the various properties of light. There we have studied polarization as one of the important property of light. You know that when you take a transparent plate of material, transparent to the wavelength which we are actually using for it to either propagate through this. If it is a window which is transparent to the wavelength, then if we shine it with a light of that wavelength through which passes through this is transparent to this wavelength, then you see normally we have always light of random polarization. So this polarization we have seen that random polarization can be resolved into two components. One that lies in the incident plane, the other which is perpendicular to the incident plane. Incident plane is the plane that contains the incident light and the normal. This is the normal and the incident light. So basically this is the plane, this board is the incident plane. So the polarization which lies this incident plane is called P polarization. And the polarization which is perpendicular to this plane is called S polarization. S polarization. So when the light falls at Brewster angle, suppose this angle is the Brewster angle, this is Brewster angle, then the parallel polarization cannot be reflected. The entire parallel polarization is transmitted, while the perpendicular polarization, that is the S polarization, is both partly reflected and partly transmitted. Partly reflected and partly transmitted, while P polarization cannot be reflected at all. So this property can be exploited to achieve coupling of the pump light into the laser cavity, just similar to what a dichroic mirror allowed us to achieve. So I end here today. Tomorrow or in the next class, we would see how this Brewster angle property of reflection of light can be exploited to achieve coupling of the incident light from a pump laser into the active media by dispensing with this expensive dichroic mirror. All right, then let us end here today.